Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. I hope you had a great lunch break and some rest for the second round of talks today. I'm David Kim from the Interactive 3D Technologies Group, and I work amongst many others at Microsoft on natural interaction and 3D technologies. And today I'd like to talk about our most recent efforts in taking 3D natural interaction out of the living room. So when we think about it, the games industry always has been the major driving force in pushing the state-of-the-art of human-computer interfaces and actually bringing these to our homes all the way to the living room. And that's not just because of the very competitive nature of the industry, but it's because of the user. The industry needs to constantly reinvent itself to keep the gamers entertained, bound, immersed into the overall gaming experience. And immersion is one of the key aspects of modern games, and we achieve this through realistic 3D graphics, through clever gameplay, and the way we mimic and incorporate parts of our physical world into the games. So joysticks, steering wheels, acceleration-based motion controllers, they're all ways to mimic the parts of our physical world and the way we interact with in our real world. But Kinect has been a major game changer that decoupled the user from a single point of input and let games observe what the user expresses with their bodies. In previous years, we worked on a number of projects that attempt to further blur the lines between the real and virtual. With Kinect Fusion, for example, we gave Kinect legs, human legs, and lets the depth sensor freely move around and understand the complex geometry of our world. We also worked on an augmented projector that combines input and output in a single sensor, and that digitally augments physical surfaces anywhere. And HoloDesk. It's a miniature holodeck that allows users to literally use their bare fingers to push pixels around. They're floating in midair. OK, so now I'll show you a few example video clips that actually shows what the system can do. So Kinect Fusion is able to reconstruct the geometry of the world, track itself, but it also sees changes happening in the environment and links physical and virtual objects together. So here the user still interacts with a real teapot, but with a virtual counterpart attached to it. So you can imagine what is possible in the future of gaming. And because we now know the 3D geometry of the environment, we can just simply let users draw and interact with like normal surfaces like the table, the wall, and ordinary surfaces, and just turn any object to a multi-touch sensor. And both the scene and the user, they're tracked simultaneously. So that allows the user to digitally interact within their own physical space, but with objects that are purely virtual. And with the augmented projector, we also decoupled the output from a single point in the room and gave it, again, human legs, which allows us to turn any surface highly interactive. So here we use a coaxial infrared camera for input sensing, motion sensors, and a pico projector in a single device and demonstrate direct interactions with shadows. And here the hand itself becomes an interactive menu, which makes object selection intuitive. And in another application, we show that the finger can turn into a pointer and a marker that lets you present and annotate slides in any room and in any surface. So we can also make paintings, graffiti, stick on specific physical locations that can be revisited later. So they just remember where they are, and the projector itself becomes kind of a digital flashlight that reveals hidden information on surfaces. In HoloDesk, we allow a user not wearing any data gloves or even digital glasses to interact with virtual objects in the same space as if they would coexist in the physical world. So the user can just touch and juggle with virtual balls and with other objects. But we are not limited to interacting with our hands. We just simply remove the glass barrier separating the pixels from the atoms, and we can use like ordinary physical objects to interact with them. And lastly, we demonstrate the use of the system as a virtual prototyping tool. So it gives the user an instant sense of the size, interaction, and the look and feel of an object that is physically non-existent yet. So one of the common themes that has driven our research has been looking at utilizing the primary tool we have to interact and manipulate in our physical world, our hands. Our goal is to unlock the expressive power of our hands and create a more natural way of interacting with user interfaces. Across the Microsoft labs around the world, we have investigated different strategies for sensing touch and enabling new forms of interaction using camera-based technologies. And we enabled more realistic surface interactions by better understanding the underlying physics in real physics-based interactions. And we made existing devices smarter and context-aware through clever placement of proximity sensors and capacitive sensors and applying machine learning algorithms. And we also enabled a freehand natural interaction on and above the surface through sensing through the display. And since the advent of our in-house depth sensor Kinect, it's now possible to interact on any arbitrary surface. We can directly interact with virtual objects as if they would coexist in our physical world. With Windows 8, we are clearly sending out the message that we are committed in making desktop interactions feel more natural and seamless. And this year, we presented a number of works around machine learning and keyboard hardware to bring that kind of interactions to our desktop space. But going forward, we want that kind of interactions, this personal computing experience, also in our everyday lives, whenever and wherever we are. So across the labs, we worked on body-worn sensors that can, to some degree, recognize certain hand poses or even sense touch through our own skin. And we also made an effort to take 3D natural interactions away from the living room and to more mobile scenarios and other scenarios. So in the following two parts of the presentation, I'll talk you through our most recent sensors for 3D natural interaction, Digits and FloodLight. So Digits is a wrist-worn sensor that captures the full 3D pose of the hand without any external sensing infrastructure or instrumenting the hand itself. And it enables both discrete gestures and continuous hand interactions on the go. So it could be used for sign language detection, for example. And so the design goals in this work were to have a continuous real-time 3D hand pose recovery with a self-contained mobile device that doesn't require any instrumentation of the hand itself. And Digits is intended for mobile use, so we had to consider aspects like the computational cost, power consumption, the form factor, and that made, unfortunately, the use of a depth sensor like a Kinect prohibitive. It's a big for you. So, so instead, we have off-the-shelf components that capture only that data that we absolutely need to with a low-power infrared laser around the wrist, a infrared camera that captures the inner side of the palm, diffuse infrared LEDs around the camera, and then motion sensing inertial measurement unit. So as you can see here, the laser projects a horizontal line across all fingers. You see there's a clear correlation between the finger band and where the laser projection lands on the finger. And to get the exact location of the projection, we first have to eliminate the infrared contribution coming from the background, from like ceiling lighting and from the sun. And to do that, we quickly capture images with and without our infrared illumination and perform a background subtraction step, which gives us the clear image of our own illumination. And then the next step is to segment these points and track them. And finally, we triangulate the 3D location of these based on the camera's intrinsic parameters and the calibrated location of the laser line. So the laser lines occasionally merge, however, when the fingers are pressed together. So to address this issue, we had proposed a digit separation and algorithm step which uses the diffusely lit image, so not the laser projected image, to detect boundaries between fingers. So at each concavity of the hand, we trace multiple vertical paths along the fingers and pick the best one using a dynamic programming approach. So at this point, we have a very sparse set of data with only 5 distance measurements, so only 1 distance measurement per finger. And from this, we want to recover a naturally looking hand model from this. So is it possible? Just some basics about fingers. A finger has 3 joints, simply abbreviated as the dip, pip, and MCP joints. And we want to know the angles to recover the overall hand shape. And we have to infer all this from a single distance measurement per hand. But scientific papers on biomechanical properties have shown that all 3 joints are interrelated when we are performing a natural fist flexing gesture like shown in the video. So in our initial forward kinematics model of the hand, we ran a simulation where we proportionally articulated all finger joints together as we would do a natural flex motion, and simulated the laser distance measurement for the hand. So the laser line, the red line shows where the laser would land on the simulated finger. And then we mapped this behavior in a graph and approximated this further in a polynomial function, which gives us a summary of the mathematical properties of this behavior, which outputs a single joint angle for a given laser distance measurement. But because there's an interrelationship between all those joints, we can simply mathematically derive the remaining 2 finger joints. So yeah, we make a really strong assumption about how you're flexing your hand. But this often holds true when we are gesturing. We don't make sudden weird movements. They are all natural and fluid. But with this approach, we can already sense discrete hand gestures, and continuous movements. So imagine you are just walking around in your house, and then it detects certain hand gestures that could be mapped to certain functions with your mobile device, for example. And the wrist sensor even allows you to comfortably hang down your hand or leave it on the surface for more subtle interactions, for example, in public areas. So while this is simple to implement, it does have some limitations. For example, our kinematics model starts to deviate from the true hand pose when we, for example, keep the knuckle joint straight, but only try to move the upper 2 joints, so a slightly less natural way of flexing the finger. And it also holds true when we do it the other way around. And to alleviate this, we came up with another inverse kinematics model, which is slightly more elaborate, and an approach to extract 2D fingertips only based on the infrared images that we already capture. So our 2D fingertip extraction uses the same diffusely lit image that we use for the digit separation and association step. And you can see here that the fingertips, the round areas, clearly stand out in the image. So we just need to find a way to computationally extract them. And so in this processing pipeline, we first generate a depth estimate of each pixel by modeling the light fall-off, by seeing how light attenuates over the distance. And then from that, we generate a normal map that reveals a depth invariant image features. And then from that, we can finally detect the fingertips through simple template matching and filtering. And so at this point, we have additional 2D fingertips and 10 measurements from a single hand. So what do we do with this? So in inverse kinematics, the angles of the joints in a kinematic chain, they can be arrived given the end effectors here. So the knuckle joint and the fingertip. However, we only have one of the end effectors, which is the knuckle. And the other one, the fingertip, is just the 2D projection of the fingertip. So we don't exactly know the exact 3D location. So the 2D fingertip could be anywhere along this ray that you see here. So we have an optimization problem here, given the laser distance measurement and a 2D position that can lie anywhere along the ray to derive the joint angle from this. And we also enable all the joints to be articulated independently. So it's like a highly complex model. But we came up with an objective function which basically minimizes the distance of the simulated laser distance measurement and the observed laser distance measurement and the observed fingertip and the simulated fingertip in a very in a brute force manner, but with a lookup table which makes it really fast in runtime. So this gives us even higher degrees of input sensing with wider range of hand poses that are difficult to predict with our simpler kinematics model. So now I'd like to show you what this kind of interactions enables in, for example, real-world applications. So one interesting interaction possibility Digits enables is 3D spatial interaction around the mobile device that is seamlessly integrated with touch input. So here the user starts semantic zooming by performing a pinch gesture and continuously controls the zoom factor. And another gesture can be used to like pan the interface or like manipulate an object after it has been selected through touch. Another interesting design space is eyes-free interaction where there's no visual feedback required. So in this example, a mobile device is left in the pocket and the user just performs a gesture to turn on the radio and mimics the turning of a dial to change the channel of the radio and changes the volume by moving an invisible slider up and down. And finally, answers a call by just simply doing a thumbs up gesture. And Digits can also be used for fine-grained 3D interactions, for example, as a wearable gaming controller. In this example, the user mimics the shape of a gun with his finger and shoots at targets and navigates within a virtual environment by just performing a grabbing gesture and moving the arm around. So Digits is currently a purely explorative research project. And I have to admit, it's a bit chunky to be used in a daily basis. It's like sticks in your clothing and stuff. So, so we experimented with other camera sensors with embedded processing and found that the tiny infrared camera that is also used in the Wii remote control that tracks infrared blobs over time and sends it via Bluetooth to another computing device. So this already shows the potential of this technology to be more in the shape of a wristwatch in future. So our latest system is called FloodLight, which was developed for 3D silhouette sensing for high precision input on and above physical surfaces. So as you can see it on the slides, there are already many ways to interact more naturally on a PC, with touch on surfaces, with a stylus for more precise input, with tracked tangible objects, and also since Kinect, leap motion, and similar sensors, also in 3D in midair. However, we need separate sensors for all these modalities, and if we want to combine them together, it's hard. They don't play well together, and all these sensors need to be calibrated to each other. So the question is it possible to combine all these modalities? So we could, for example, use a depth sensor like Kinect or similar sensors, but they don't offer the necessary precision as they were developed with tracking coarse body motions in mind. And a 3D motion controller like leap motion, they are quite precise, but they are only limited to tracking fingertips that are in midair. So motivated by this problem, we accepted the challenge and we developed FloodLight. So FloodLight is a single sensor for robust, pressure-enabled touch, stylus, tangible objects, and mid-air interaction. And here we demonstrate the manipulation of virtual objects using on-surface and as well as mid-air gestures. And we can also use custom physical widgets like this color wheel to control parts of the user interface. And we also allow for more precise input with pen or any other pen-shaped objects. So by letting users seamlessly switch between pen, touch, and freehand 3D interactions, as well as the use of physical interaction widgets, FloodLight offers a really extremely rich interactions in a variety of styles within a single package. So here, a little trackpad is used to control the camera of the scene. And the hardware setup itself is fairly simple. It's cheap and it's fairly easy to reproduce. So here we use a pair of infrared cameras, diffuse infrared LEDs, and off-the-shelf retroreflective material, a material that can be found on sportswear or like on bicycles. And this material just aids the segmentation of objects by enhancing the contrast in the camera images for objects that are positioned between the camera and the surface. So the property of this material is that light coming from other sources, they will simply bounce back, and only light shot from the direction of the camera will bounce back to the camera. So, so with this simple trick with optics, we can keep all the smarts in the camera and leave the whole interaction and touch area free from any electronics. So that reflective material is also tracked, and we can sense 3D contours of the hand above the surface. And we can also extract the fingertips, as well as their pointing directions. And we can also extend this mechanism to even detect pen and other pen-shaped objects. And when tracking hands and fingers, FloodLight also offers touch detection with sub-millimeter accuracy, and as well as information about the distance of the fingers relative to the surface it's interacting with. So it gives us hover state. And we can also reconstruct the full depth map from the 3D contours of the tracked objects, for example, for more sophisticated applications. So this is the image processing pipeline in motion. So we see two rectified images from the stereo cameras. This is all the input signal we get from the FloodLight system. And the objects placed on top of the retroreflector, they can easily segment it by masking out the convex hull of the reflective material. And once the objects are segmented from the background, our novel stereo algorithm efficiently recovers the depth from these contours, and which we visualize here in false color mapping. And we can also interpolate the depth between the contour points. So the 3D motion tracking is very robust and fast, only because our images are virtually already segmented and binarized. We have a clear segmentation. And in our processing pipeline, we simply trace the contour of the objects and don't use the whole image. So we don't use all the megapixels of the camera images, but only use the contour points to extract the depth. And this simply removes the need to do a search over the whole image and make this approach unique and very fast. And the contour path is also used for some post-processing steps, for example, smoothing and filling in some missing measurements. So in detail, the stereo matching algorithm works like this. So we extract the horizontal disparity of a certain contour point as observed from the left and right camera. So we have the contour here, and we have one from the left and from the right camera. And we look for the disparity, the difference between the two images in parallel for all the rows. And as there can be many other contour points in the single row, for example, 2 contour points for a single finger and 10 contour points for 5 fingers, we have to test for their compatibility to make sure that we are observing the same point on the silhouette from the 2 images. And so the compatibility is tested just based on the direction of the contour point and their location relative to the contour they sit in. And this is a combinatorial problem, and we solve it again with a dynamic programming approach, which gives us the best solution for all contour points along the row. So in the diagram right, we see the contour points ordered by their x direction in the x-axis, and the contour points from the right image in the y-axis. And with this cost matrix, we can simply trace the path with the lowest cost and find the best combination of matching the left and right contour images together. So the precision we get from FloodLight, FloodLight's depth estimation also enables a variety of features. For example, with a malleable reflective surface, we can detect hover, touch, as well as pressure information. So the blue column you see is the amount of pressure you put in. And we can also use FloodLight to detect and track pen or pen-like objects for like drawing applications. And this enables a precision quite similar to common graphics tablets. And the robust tracking also extends to physical objects in 3D space, allowing us to directly manipulate virtual objects that are mapped to physical tokens. So to get a better sense of the performance of FloodLight with real users, we conducted a comparative study with to evaluate the 3D pointing task with other state-of-the-art commercially available systems. So we compared FloodLight to Kinect with FloodLight's fingertip detection pipeline, which we call Kinect Lite, and to Leap Motion, and 3D gear system, which also utilizes the Kinect to detect certain hand poses. And we conducted the study with 12 participants, and we had 3,888 selections in total. And maybe not that surprisingly, FloodLight performed the best, requiring only 1.95 by 1.55 centimeters, approximately the width of the finger, for the minimum target size, which is shown here on the left in black. Closely followed by Kinect Lite, and then Leap Motion and 3-gear system, which requires a minimum target size of 5.3 by 3.15 centimeters. And we also compared their touch accuracy in a separate second study. And we asked participants to touch 12 grid points on a plane. And here we came up with a new physical setup where we enabled touch sensing even for the Kinect and Leap Motions, which were originally not intended for touch sensing. So we used an infrared absorbent paint, a sheet for the Leap Motion, as you can see here on the bottom picture, and a transparent acrylic for the Kinect setup with laser-edged touch points. And this study also yielded similar results to the first study. FloodLight ranked first, followed by Kinect Lite, and then Leap Motion, and 3-gear systems. So FloodLight is a very flexible sensor platform, and there are so many ways to avenues we can follow in our research, in our future research. And as I said before, all the smarts in FloodLight are in the camera itself. So we could allow users to simply augment any existing physical device with touch and proximity awareness. And we can let users to simply cut and shape a virtually infinite number of input devices, like a 3D multi-touch mouse, a 3D trackpad, sensor strip, touchpads, buttons, and more. And in an experiment, we also found that common printer ink is transparent in the infrared spectrum. So they don't show up in the input images. So we can simply visually augment the reflectors with a custom user interface. So the computation part of FloodLight is fairly lightweight, which means that the whole system could be ported to a mobile device like a tablet and mobile phone. And with 3D input, user user interaction wouldn't be any more limited to the physical size of the device itself. We can just use the whole 3D space around the user. And again, we did some initial experiments and found that the camera and the built-in LED flash in mobile devices already give us a very strong signal. So both videos were taken simultaneously, and here we can see on the right that the retroreflective material only appears as a strong signal on the camera with the LED flash turned on. And in the other camera, we don't even see the LED flash turned on. So the signal is strong enough for the sensor to pick up, but it wouldn't disturb or blind the user from like normally interacting in the same space. And we very recently we got hold of a phone with a stereo camera and LED flash very close to the lenses, and so we again did a quick experiment and found that in the two images the reflective material again sticks out fairly brightly. So we can just, for example, in a mobile use, we could have a smartphone which we carry around along with some other DIY widgets and like malleable sheets that you put in your pocket, and you could have access to 3D interaction anywhere. But potentially, we don't even require a stereo camera phones. We also investigated utilizing only a single mobile phone in floodlights. We could use small mirrors and a red, green, blue splitting prism that is commonly used in the 3 LCD projectors and cameras. And we could just encode the left and right images of the scene into the 2 different color channels in an RGB image. And we wouldn't sacrifice on the field of view or the number of pixels to capture left and right images with a single sensor. Okay, so now I'd like to conclude this talk with a fairly simple sounding question. What is the future of desktop interaction? We don't know it yet, but we've tried to hook up FloodLight to Windows 8 anyway. So interactions work seamlessly with all multi-touch enabled apps. So this is Bing Maps in Internet Explorer, and we could just use normal multi-touch interactions on it for smooth navigation. But we can also use mid-air gestures for gaming scenarios, for example. And with a printed keyboard layout on top of the reflector, we can also type on it if we really want to, if we want to keep our hands on this interactive area. And then after finished typing, we can simply switch back to multi-touch mode and continue with our natural interactions. And finally, we let users reach for and grasp objects in a virtual environment that mimics the behavior of our own physical world. So will any of this really take off? I think we'll have to see and wait. And with that, I'll finish my talk and take your questions.
Any questions? Yep, at the back there.
Is it conceivable that the thing that is on the desk that you're interacting with could actually also be a screen so that you could project different things up, like that keyboard or some other stuff?
Yeah, so really interesting thing about the retroreflector is that it is highly angle dependent, so it's really good for the sensor. But for the output, it would be really bad. But there's one way to have a really good output, and that's by putting a pico projector next to the eye. So, for example, by having 2 pico projectors like next to your eyes, you could have stereo 3D output without like having anything in front of your eyes, just by putting the projectors on the either side of the eyes. So that could be used, but we can also use a normal LCD to use similar kind of interactions. I don't know if you've noticed, but you can use a polarizing filter like the one in 3D cinema glasses, and then point it at an LCD display, and then the LCD just turns black. You don't see any light coming from the display but the hand. And so we could use a glass screen and use cameras with these polarizing filters on top. and then could have, again, have really clean segmentation of the hand itself. So we can, so the 3D contour sensing is not limited to the reflective materials, but there are so many ways to get a similar result with other ways of segmenting the foreground from the background.
Okay, any other questions? Very good. Thanks again. Really appreciate that.
Thank you.